to look at a time response of second order systems. This is a very important lecture and is the continuity of lecture 11, where we focused only on first order systems. Now we're going to see how second order systems behave, and the analysis is slightly more complicated because they have many different cases to study. But it's still relatively simple and yet very important when you want to design to control a system. We need to understand well how the system behaves and also how we will affect that behavior by controlling it. Our controller may make an unstable system unstable or an unstable system stable. We may induce oscillations in a system that would otherwise not have oscillations. We may remove oscillations from a system by using a controller. So all these we can see in a second order transfer function. And today we're going to look at exactly which elements in this transfer function will give the behavior of the system in terms of oscillations, in terms of exponential convergence, etc. In the past lectures, we were analyzing the two phases of a system. The first one is the transient responses, how a system starts and goes towards a settling point. And then the second part is the steady state. The steady state is reached once the system stops moving, once the system has reached its final value. And we can use the final value theorem to determine that specific value. Now, the transient depends on many different things. It depends on the order of the system and depends on the characteristics of that transfer function. In the last lecture, we were looking at first order systems, and we saw that for first order systems, the time response is always an exponential waveform. Why is that? Do you remember from lecture 11, why do we always have exponential waveforms?
The way the time constant interacts with the exponent e.
Right. Is the way the denominator of the transfer function becomes an exponential. The time constant is a real number. The poles of that transfer function are always real numbers. Therefore, when you take the inverse, we always have exponential curves. The sinusoidal component, there are no imaginary components in the poles of first order transfer functions, which is the same way to say what we just said. Now, when we look at second order systems, we may still have exponential components, but we can also start to see these oscillations. And if you look at these oscillations, we have some sort of sinusoidal component that decays over time. And that what makes it decay is precisely the exponential component. So now we can go from having an exponential to having an exponential plus a sinusoidal or even just a sinusoidal. And the system may even become unstable. All of this will depend on how the poles of the transfer function are in a second order system. You remember that for a first order system, we wrote the standard form of the transfer function as k divided by 1 tau s plus 1, where tau is indeed the time constant, k is a constant, and here the poles of this transfer function are always negative 1 over tau, where tau is a real number. Now for the second order system, here is the standard form we want to use. We use the standard form for the first order system so we could see clearly how fast the system responds by highlighting the time constant. And here we are doing a similar analysis. All these constants that appear, or these variables that appear in the transfer function, they have a function there, and we want to highlight them because we know that they affect a specific thing in the time response. We have omega n squared divided by s squared plus 2 zeta omega n times s plus omega n squared. So we see two distinct variables here. The first one is this zeta. And zeta is what we're going to call the damping ratio. And this is a very important concept we're going to use throughout the lecture. It's the damping ratio, and it has no dimension. It's just a constant number. And we have also omega n, and omega n is the what we call the natural frequency of the system in radians per second. Okay, so two variables in a second order transfer function now: omega n, the natural frequency, and zeta, the damping ratio. And this is the standard form. Where does this standard form come from? Well, this is a little mathematical trick that will help us understand how the system behaves by simply looking at the value for zeta and omega n. And based on that, we know if the system have oscillations or not. So now that I have a second order transfer function, we can simply equate this transfer function to 0 and solve for the poles of this transfer function. Now we have three distinct cases here. We can have real numbers, as was the case for the first order system. We have two roots always. We can have complex conjugate numbers, or we can have purely imaginary numbers. These values will depend now on the parameters omega n and zeta, specifically more on zeta than omega n. And of course, now that we have three distinct sets of poles, we will have three distinct temporal responses that can arise from the same transfer function. Let's consider this example here. We have the standard form for the transfer function, and we have a mass spring damper system. In the mass spring damper system, the input in this case is the force applied to the mass, and the output is the displacement. If we do the transfer function between force and displacement, we get this equation, right? The well-known equation. For now, what are the damping ratio and the natural frequency of this function? Well, it's easy. First, we can equate all the elements in this transfer function with the standard form. Let's start with what multiplies s squared. It's 1. We have 1 times s squared. And in our transfer function, we have m times s squared. So already we don't have the exact same format. We need to get rid of that m first. This is very important. Never forget to do that. If you divide the entire transfer function by 1 over m, we have 1 over s squared plus b over m s plus k over m. If you multiply this out, we'll go back to the same value. And now we have 1 and 1 in front of s squared. So now we can compare the other elements. We can omega squared is the term that it doesn't multiply s, and here it is k over m.
Sorry, Professor, why did you divide by 1 over m? Over r?
What I wanted to do was to get rid of this m here in front of s, because what multiplies s squared, in the standard form is 1.
Oh,
so to get 1 there, divided by 1 over n.
Okay.
I will multiply by 1 over n. Okay. So now we can equate all the elements. So omega n squared is equal to k over m. Omega n is the square root of k over m. And for the damping ratio, we can equate this part that multiplies s with everything else that multiplies s here. And there we have, let me start something new here, 2 zeta omega n equals to b over m. We can also solve for zeta. Zeta equals to b over 2 omega n. Zeta equals to, you'll notice that every time I write zeta, it comes out differently. B over 2 square root omega n. Omega n times m, and I provide here, k over m times m. Okay, now we have the two elements of interest, omega n and zeta, defined by this transfer function. Okay, the damping ratio and natural frequency, both functions of the characteristics of the system itself, that is viscous friction, the mass, and the spring constant. Why exactly do we need to know the damping ratio and natural frequency? We'll get to that. So back to the message here, I just wanted to clarify, just don't forget to, when you compare this transfer function and you put in the standard form, don't forget that what multiplies s squared is always 1. So do prepare the transfer function in that format. Now, if we have a second order transfer function, we can find the poles of this transfer function. And to find the poles, we can simply find the roots of the denominator using the quadratic equation. Here is the quadratic equation, minus 2b plus minus the square root of 2ac squared minus 4c. Minus b squared, sorry, minus 4c divided by 2. So this is just the quadratic equation using the elements that we have there. And when you solve for this, you see that inside of the square root, we have omega squared. We can factor that out and take that out of the square root. So it shows up here. And these are now the roots of this transfer function, of this denominator, which are the poles of the transfer function. You see that they can be now real or imaginary, depending on the value of zeta. Because zeta is inside that square root. If zeta is greater or smaller than 1, that will affect the type of roots we have. We have two roots, the second order polynomial. So one will take the positive sign, and the other one will take the negative sign. Right? So two roots now that depend on the imaginary and on the real part of the number. You'll notice there's a slight difference here between what is inside of the square root. Right? What I simply did here was to multiply everything by -1. So you have square root of zeta squared minus 1, which is the same as the square root of -1 times negative zeta squared minus plus 1. Right? -1, the square root of -1 is the complex variable j times 1 minus zeta squared. Okay, so just a small manipulation here. The reason being is that I can clearly show that we may have a imaginary component in the time response now. Okay, so two roots that may or may not have imaginary components. What do they depend on? Well, if you look at the roots here, that only depends on the value of zeta. If zeta is greater or smaller than 1, we may have this as being a complex number or not. And so it can go from only real to imaginary to complex conjugate numbers, depending now on the value of zeta. This is simply the application of the quadratic equation to the denominator of the transfer function. Any questions here? No? Okay, so now let's take this expression that we established for the poles and see what happens to the system when we vary zeta. I can go from a negative to a positive number. And let's see what happens there. So the first case you need to consider now, and we have considered a few cases. The first one is what you're going to call, and this is a very important term that we need to keep in mind, is a overdamped system. In this case, zeta is greater or equal to 1. I would say just greater than 1. Let's call that greater than 1. Shouldn't be equal. Equal is a separate one. So zeta is greater than 1, which means in practice there's a lot of damping happening in the system. If that is the case, then what happens to our roots? We'll see that a zeta squared minus 1 is greater than 0 when zeta is greater than 1. Is this clear? If zeta is greater than 1, then zeta squared minus 1 is greater than 0. Yeah?
Yep.
Yeah. Which means that the result here is a positive number. And if the positive number is inside of the square root, then we end up with two real roots. We end up with two real roots, positive or negative. But in this case, because the system has a damping ratio of greater than 1, the roots will always be a negative number, meaning that A1 and A2 will be always greater than 0. We can, because we have two distinct numbers, two distinct real roots, we can rewrite the expression as, let's say, a constant divided by s plus a1, s plus a2, or a1 and a2 are these constants that will solve for the roots of the polynomial. And you can now split that into a exponential, into a partial fraction expansion. And when you expand that into partial fraction expansion, this is what you get: k divided by a plus a constant divided by k2 divided by plus a k2 divided by s plus another constant. And a1 and a2 will always be greater than 0. This means that when you take the inverse Laplace, this is what we see: 2 exponentials, 1 for each pole. 2 poles, 2 real poles, inverse Laplace, 2 exponentials, 1 for each pole. What can we conclude here? We can conclude that we have no imaginary components in the time response. We have 2 poles. Each pole is real. Each pole generates its own exponential. No sinusoidal component. The system is overdamped. It will behave as a first order system in the sense that its time response is an exponential component. What else can we say? We can say that because a1 and a2 are greater than 0, when you take the inverse Laplace transform, we'll notice that on top of the exponential here, we have a negative constant times time, meaning that as time tends to infinity, they go to 0. All exponentials will go to 0. Okay. So the main message then is, because the real part of the poles is negative, remember that the poles of this transfer function are negative a1 and negative a2. They are located on the left side of the S-plane. The real part is located on the left side of the S-plane. The exponentials they create will decay to 0. The system converges to a steady state value. And this is the case for overdamped systems. Any questions here?
Can you just repeat that last part with the graph, sorry?
Yeah, so let me actually maybe move here, and that will be a bit more clear. The poles of our transfer function are real negative numbers. S equals to negative a1 and s equals to negative a2. So when you put them on the S-plane, they lie on the left side of the S-plane. They are real numbers lying on the left side of the S-plane. Each of them generates an exponential curve. Each of them generates an exponential curve that it decays over time and will tend to 0. So their transients will eventually tend to 0 because of the negative exponential times time. Okay. When now we plot the time response, considering that a mass spring damper system again to a step input for the system, here we have different parameters. We remember that the damping ratio was directly a function of the damping coefficient. So if we increase the damping coefficient, we are increasing the damping ratio. And you see that the more we increase the damping ratio, the more of an exponential curve we are getting. And as the damping ratio decreases, you see that this exponential is getting less and less pronounced. Okay, and look at the poles. The poles are always located at the left side, on the left side of the S-plane, and they still generate a time response. So as we decrease the damping ratio, see that the poles are getting closer and closer together. And when zeta is 1, the 2 poles will be exactly the same. When zeta is 1, the 2 poles will be exactly the same, but it's still lying on the real side, on the real axis on the left side, creating an exponential that decays to 0. Okay, so this is the first case, a overdamped system. So let's summarize. In an overdamped system, the roots are, or the polynomial or the poles are both real and distinct from one another. They create exponential components. Each exponential component decays to 0 because the poles will lie on the left side of the S-plane because their real part is negative. Okay. So as we keep decreasing the damping ratio, when you reach 1, zeta equals to 1, we see that the two poles meet together there. And this is the second case we want to study. This is the so-called critically damped system. In a critically damped system, we reach the condition when zeta is exactly 1. The damping ratio is exactly 1. And when now we put a zeta equals to 1 here and here, you see that this part of the square root is 0. And we are left with two distinct roots. Sorry, two identical roots. This means that we can now write the transfer function as, and the roots are omega n squared, right? When zeta is 0, we are left with, sorry, zeta is 1, we are left with, so this is 1, this is 1, this is 0 and 0, we are left with negative omega n for both of them. So the transfer function can be written as a constant divided by s plus omega n, which is s plus omega n squared. And this is what we get. Now we have to do partial fraction decomposition. And when you do partial fraction decomposition, we have expression number 7. One constant divided by s plus omega n squared plus another constant divided by s plus omega n. And notice that again, once you take the inverse Laplace transform, we are left with an exponential component. And both exponential components decay eventually to 0. Because the poles are identical, but they are still real numbers, real negative numbers, and they lie on the left side of the S-point. Now, visually, there is no way to distinguish a overdamped system and a critically damped system because they are still exponential components. But what are we doing? We are decreasing the damping ratio slowly, and you see that the system is getting a bit faster and faster. Right? So the critically damped system is the point, that's why it's called critically damped, is the point where if we decrease the damping ratio more, we will start to see oscillations. That happens when zero. Exactly. Any questions so far? No? All right, so let's continue now. Now we are with the underdamped system. We kept decreasing zeta, and now we reached a point where zeta is less than 1, but greater than 0. Zeta is less than 1, but greater than 0. This is called the underdamped system, meaning that now damping is smaller than the overdamped. It's smaller than the critically damped. We are now in a range between 0 and 1. If the zeta is indeed between 0 and 1, then what happens? Well, we can input zeta here. And if zeta is indeed between 0 and 1, then the summation, or the zeta squared minus 1 inside of the square root is negative. These two will become negative numbers, meaning that you have a square root of a negative number, and the square root of a negative number is an imaginary number. Now I have two components. One component that comes from this multiplication that is real, and a second component that will come from this multiplication that will be an imaginary number. We now have two elements in the whole, a real and a complex number. We have complex conjugate numbers, meaning that their real part will be the same, always the same, and their imaginary part will be the conjugate of the other, something like 1 plus minus 2j, 1 plus minus 5j, 5 plus minus 3j. The real part is always the same. The imaginary part is always a complex conjugate of the other. When you have that, and you try to do the inverse Laplace, I'm going to skip that part, but we will see always an equation like this. we now have a lot going on here. We have a exponential part, here it is, that comes from the real part of the pole. And we have a sinusoidal component that comes from the imaginary part of the pole, and they multiply one another. What else can we see? We can see that the real part of the pole is still negative. The real part of the pole is still negative, meaning that the exponentials will eventually decay to zero. And that's what we see here. We see that what multiplies t in the exponential is a negative number. So as that goes to infinity, t goes to infinity, the whole part goes to zero, which brings the entire part of the system to zero. So we have two components. The second component always oscillates, but is multiplied by an exponential component that in turn decays slowly to zero. So the whole thing eventually decays to zero. And why? Because the real part of the pole is negative. This is what it looks like. If you keep decreasing the damping ratio, now notice that we are at 0.75, at 0.5, 0.25, and 0.05. Notice how the poles are moving. We have now complex conjugate poles. So before we are sitting on the real axis, now we have complex conjugate poles. We broke away from the real axis and we have now complex conjugate numbers as poles, and they have both a real and an imaginary component. Each of them gives raise to an exponential and a sinusoidal component. And notice how now these oscillations showing up in the step response of the system. And these oscillations get more and more pronounced, the smaller the damping ratio. And the smaller the damping ratio, also notice that the poles are moving closer and closer to the imaginary axis. They are tending to a purely imaginary component. See how the real part slowly decreases. We can clearly see this in the last one, because here you see the exponential component. This is the envelope here is an exponential component times a constant. And you see that inside of that envelope, we have a sinusoidal waveform. But because they multiply one another, then it's low here. Okay, so this is the third case, is a underdamped system, not enough damping to create an exponential waveform only. There will be some oscillations. These oscillations come from the fact that now we have real components in the poles. Question? Any questions here?
What did you say about oscillations again?
Where do you see the oscillations?
You said something about oscillations are because of real numbers.
The oscillations are because of complex numbers. So let's go back here. So we have now poles that have so this is less than zero, meaning that this part and this part are imaginary numbers, right? Whereas the first part here is a real number. So the poles will be in the form of sigma plus minus j omega, and now sigma is the real part, omega n is the complex part. The real part gives always an exponential. Here is the exponential that comes from that. The imaginary part gives always a sinusoidal. Here it is. So we have a sinusoidal, we have an exponential that in this case decays to zero, and when we combine them, we have a exponentially decaying sinusoidal waveform, because they multiply one another. Okay, so the sinusoidal comes from the imaginary, the exponential always comes from the real part. And once again, because the real part is negative and lies on the left side of the S-plane, then the exponential decays to zero as time goes to infinity, and the entire system will eventually tend to zero. Any other questions?
Professor, so in the real situation, is that means it's better to avoid the oscillations?
Not necessarily. It depends on the application. If you want the system to react faster, you can consider some oscillations. Let's say this system here. If you had a first order system, you would very likely have a system going like that.
Oh, yeah.
All right, so it's slower, but doesn't oscillate. But maybe you can afford some oscillations. And if you can afford some oscillations, your system reacts faster. There are examples where we don't want oscillations. Let's say there's a position control of a robotic arm that operates on the eye, for example. And if that is the case, we want to reach, say, this position here, 1. We want to move it by 1 millimeter. If the system reacts too fast, it will overshoot and go to 1.5 millimeters before it settles at 1 millimeter. So you may have basically puncturing the eye. Right? Whereas the exponential never exceeds 1.
Okay, I got it. Thank you.
But it's slower. So it really depends on the application. If you want to control the drug content in the body, for example, you don't want to overshoot. You don't want to overdose. So that would also be preferable to have a slower system, but overdamped.
Got it. Thank you.
I have a question. So you said as it reaches infinity, the function would decay to 0. So does that mean like these exponential or like these graphs, they'd eventually like go back down?
No, these graphs are the time response of the system to a step input. So the step input always remains, but the transients that are generated by the allocation of poles, they eventually disappear. Right? Only the transient disappears. The steady state is not necessarily 0.
Oh, so it's like basically it just kind of stops increasing to like where the step function is.
Yeah, so let's put it this way. If you have the mass spring damper system again, we are applying force F of S, and the force F of S is a step. So which means that it will start at 1, let's say at times 0, and go to infinity at 1. Right? The system will respond like this. It will reach a certain steady state value. And once that steady state value is reached, it will stop, but it will reach that steady state through a transient, and the transient depends on where the poles
are. Okay, thank you.
Yeah. So all of these are a step. If you're looking at an impulse, then it would be different. It would just go to 0 like that. It would go to 0 like this, and it would go to 0 like that, and so on. Right? But now here we're looking at a step. So what makes it not go to 0 is the step input, is not the location of poles. Any other questions?
Sorry, someone asked in the chat if the poles are negative for both overdamped and critically damped systems.
Good question. So the poles, for everything we have seen so far, they have negative. The pole's negative doesn't really mean anything, but the real part of the pole is negative. For everything we have seen so far, the real part of the pole is negative, and that's why exactly all the exponentials that we created here, they are going to 0. You notice that everything is exponential of negative something times t. So the real part of the pole for the overdamped, the critically damped, and underdamped systems is always negative. The real part makes the poles lie on the left side of the S-plane. Okay. Now let's continue our analysis, and you see here that as we are decreasing the value of zeta, the poles are moving towards the imaginary axis, and we will eventually reach the imaginary axis, and that will occur precisely when zeta equals to 0. When zeta equals to 0, we call the system undamped, and in this case, nothing dissipates energy in the system anymore. The system is undamped. And if zeta equals to 0, this is 0, this is 0, this is 0, this is 0, and we are left with negative, we are left with omega times the square root of -1, that is j omega n. Omega n times negative square root of j sorry, negative j, or negative square root of -1 is negative j omega n. And now you see here that the real part of the pole is 0. The imaginary part of the pole is not 0. So the exponential is gone. And now we turn the system into something that only has imaginary components. How should the time response be? What kind of
It
waveform?
will never converge. It will keep going up and down and up and down.
Exactly, exactly. It will always converge. It will never settle because the exponential parts are gone. If we have now two complex roots, we can write the system in this format and then expand that into partial fraction. We don't even have to actually, you can just solve for it, but you see here that the roots are only purely imaginary. And when you take the inverse Laplace, for this specific example, we see that there's only a sinusoidal component, cosine of omega t, and the system only oscillates. Okay, there's no exponential, there is no real part in the poles. Where are the poles exactly? Well, now they lie on the imaginary axis. They lie on the imaginary axis because their real part is 0. Look at the time response. The system always oscillates and never settles. It will oscillate at a very particular frequency. And this frequency of oscillation in the undamped system is precisely how we define the natural frequency. In other words, the natural frequency that we define for the mass spring damper system as a square root of k over m is the frequency the system oscillates at when there is no friction. Is the undamped frequency of oscillation. That's the natural frequency of the system. How do we reach a point where there is where you have a damping ratio of 0? Remember that the damping ratio is directly related to the energy dissipation. So if you take the system, the mass spring damper system again, and we set the damping to 0, we are left with a mass and a spring. So there's nothing dissipating energy in the system. Once you apply a force to it, we are creating kinetic energy because the mass accelerates and has a speed. That kinetic energy stretches the spring, stores potential energy. So kinetic energy goes to potential energy goes back into kinetic energy, back and forth. The system oscillates, and in the process of transferring energy from one form to another, there is nothing dissipating energy, and the system oscillates indefinitely. If we had damping, then in the process of transferring energy from one part to another, some energy is lost, and eventually the system settles at 0. And so the more damping, the more energy is lost, the faster it will eventually reach 0. And we'll see the system going from an exponential to sinusoidal with exponential to something like this when we completely eliminate friction. Right? And now the poles are lying on the imaginary axis. Let's change now the frequency of oscillations. If we change now the spring, we set zeta to 0, so B to 0, and we now change the mass of the system, we are changing the natural frequency. And you see that the frequency at which the system oscillates is changing, is decreasing as we increase the mass. And you see that the poles move towards the real axis now. The closer they are to the real axis, the smaller the frequency, because these values here are the values of omega n. Now this is j omega n, and this is negative j omega n. And omega n is the frequency of oscillation. So the closer you are to the real axis, the smaller the number, the lower the frequency of oscillations. The farther you are, the faster the system oscillates. Okay, so this is the fourth case. Fourth case where there is no damping at all and the system oscillates indefinitely. Are we good? Anything here? No?
Professor, did you say that the closer you are to the real axis, the faster the system oscillates?
The slower the system oscillates. Because these values again of sorry, didn't mean to do that. The poles are a j omega and negative j omega, omega n. Right, so these values here are basically omega n, negative omega n. So the closer, the smaller omega n, the closer you get to the imaginary, to the real axis, the slower the system oscillates. Now you see how we go from these different frequencies, and you see that the poles are getting closer to the imaginary, to the real axis. Okay.
Professor, so like the speed or the displacement of the system related both of the mass and the frequency?
The natural frequency depends on the mass and on the spring constant.
I mean that omega n.
Omega n, yes, omega n is a direct function of k and n.
Oh, okay.
Okay,
Professor, is this a general thing, or does this only apply to the system?
This applies to any second order system. I'm using the mass spring damper system as an example, but it applies to any system, any second order system. Last case here, let's look at a case where the damping ratio is less than 0. And this is an unstable system. How do we get a damping ratio of less than 0? Well, technically, that only happens if you have a hypothetical negative damping, which is pretty much impossible because that would be free energy. But we can make a system with a negative damping ratio if you are actively controlling it in the wrong way and making it go unstable. So when you do this now, what is happening? We can have still complex or complex or real numbers, but there is a distinct difference. When the damping ratio is smaller than 0, then notice that the real part of the pole is now positive. Right? Omega n times negative zeta. When zeta is smaller than 0, the real part of the pole is greater than 0. Same with this one. The real part of the other pole will be greater than 0. Which means that when you now take the inverse Laplace transform, we will get either a purely exponential waveform if you have complex real numbers only, or a sinusoidal and exponential if you have complex values. But both of them have now an exponential that multiplies t with a positive number. This will make now the system diverge and tends to infinity. You see that the exponentials, as time goes to infinity, also go to infinity. The system increases indefinitely, it never settles. And this characterizes an unstable system. Why again? Because now the real part of the poles are positive. The poles are now sitting on the right side of the S-plane. And this is the exponentials that they create. Instead of decaying to 0, they go to infinity with time. And the system is said to be unstable. Notice that what makes the system unstable is not the exponential, it's not the sinusoidal. The sinusoidal is still there, but it's still oscillating indefinitely. But now it's getting bigger over time because the exponential grows over time. So if zeta is greater than 0, is smaller than 0, but greater than negative 1, smaller than 0 and is smaller than negative 1, so we'll just do it the other way. So it's smaller than 0, but greater than negative 1, then we have a sinusoidal and an exponential with the exponential going to infinity. If zeta is smaller than negative 1, then now we have only real numbers as poles, but they have positive real parts, and everything is only exponential going to infinity. Okay. Are there any questions?
Professor,
Mhm.
do we have this situation that zeta equals to -1?
Zeta equals to -1. Yes, it would also, we could have that. It would also be characterized by an exponential form, waveform, that goes up to infinity. Yeah.
Okay.
Would be the same as the critically damped, but now there is no, it's just an unstable system. A unstable is unstable regardless if it has exponential, sinusoidal, or whatever.
Okay, thank you.
They don't need to worry about that specific case. So we have 5 distinct cases. And here is what we see in these examples. Now, if you have only exponential waveforms, they go to infinity like that. Now the poles are purely real numbers, but I have positive real parts. And in case we have complex conjugate numbers with positive real parts, then now we have an exponential and a sinusoidal. And you see now the exponential is growing to infinity and bringing with it to infinity the sinusoidal component. And the system is unstable for both cases. Okay, so let's summarize all this. With all cases we discussed so far. So we saw 5 cases. Let's try to, I'll just draw it here. Hopefully this is straight. That's not, of course. And let's see the location of the poles, and let's see what happens to the time response. Let's summarize the entire system. So on the top here we have the imaginary axis. The bottom here is the real axis. When we started looking at first order systems, we defined that the first order system will have poles being placed always on the real axis, either on this side of the real axis or on that side of the real axis. Let's start here. For the second order system, we always have 2 pairs of 2 poles, 1 pair of poles. They are both real if zeta is greater than 1. And zeta is greater than 1, we have two distinct poles. They lie on the real axis. They have negative real parts, and the time response they create is a exponential waveform like this. So for a step input, this would be the time response for a impulse input. Right, so this is case number 1, where zeta is greater than 0. As we start to decrease zeta and you reach a point where zeta is exactly 1, then we now have 2 poles that are exactly the same. They're exactly the same, but they are now still real numbers and they still lie on the left side of the S-plane. So the real parts are negative. Because of that, we have the same time response, an exponential that decays to 0. So here is the step and the impulse response for those systems. There is no way to distinguish them visually. They will always be. If you keep decreasing the damping ratio, we reach a point where now the poles will break away from the real axis and they become complex conjugate. Meaning now that they have both an exponential and, both a real part and an imaginary part. This occurs when zeta is less than 1 and greater than 0. Okay, so imaginary component, real component. The real component is still negative. It still lies on the left side of the S-plane, meaning that their exponentials will die to 0. And the time response for a step input will now have both sinusoidal and real components, like that. And the time response to a step, as there, the time response for a impulse will be something like this. Now this will be the third case there. As we keep decreasing the damping ratio more and more, the imaginary part is tending to the real axis is tending to 0, and eventually we'll reach a point where we have two complex conjugate poles here and here. This will occur when zeta equals to 0. And because now the exponential component disappeared, because the poles are only imaginary and the real part disappeared, we only have in the time response a sinusoidal waveform that never decays. This is the undamped system. If you keep decreasing zeta now to a point where we are less than 0, but it's still greater than 1, greater than -1, we are breaking into the unstable zone, because now the poles have both the real and imaginary component, but now the real component has a positive real part. So this would be the case where zeta is smaller than 0, but greater than -1. And now the exponential generated by these guys, it will grow to infinity, like that. And finally, if you keep decreasing zeta, we reach a point where zeta is smaller than -1. We are now to the other side of the problem here. We only have exponential waveforms, but these exponential waveforms grow to infinity. Okay, this is summarized in this slide that you have here in the next one.
Professor, sorry for the last one. There should be 2 roots.
Should be 2 roots, yeah.
Okay, thank you. So if it is equals to -1, there is only 1 root, right?
No, this is always 2 roots, but they are the same.
Oh, okay. Yeah, you're right. Thank you.
Okay, so this is the entire picture of the system now. As we change, in the case of the mass spring damper system, the only parameter we would have to change to move from a completely underdamped system to a fully unstable system is the friction coefficient B, that it directly affects the damping ratio. Okay, so what can we conclude from all this? Well, if you want to know how the system behaves in the time domain, well, what do you need to know? The damping ratio. That's all we need to know. We don't even need to take the inverse Laplace of the system to know exactly how it's going to behave. Because if we know the damping ratio, we know what kind of temporal response the system will assume. How fast are these oscillations going to happen? Well, then look at omega n. Omega n tells us the frequency of oscillations of the undamped system. So to summarize, overdamped, lots of damping. Critically damped is still lots of damping, but we are to the point where the system will become underdamped. Underdamped, not enough system damping, so we start to see oscillations. Undamped system, no damping at all, only oscillations. And then anything that lies on this side of the S-plane is unstable and has no interest for us. Any questions? It's not very hard, is it? What do you guys think?
It's okay for me.
Yeah?
Looks good.
Okay. All right. So if there are no further questions, I think that's pretty much it all. Let's do exercise 1. Let's consider the, remember a few lectures ago, we worked on a muscle model, and the muscle model was represented by a mass spring damper system. So now let's take that model and see here that is given by this transfer function. And we have one parameter that we can control, and that is the damping coefficient in that muscle model, B. And let's find the temporal response of this system to a step input when we vary the value of b. Let's see how that works. So the first case would be when b equals to 9. So replace b with 9, find the damping ratio, the natural frequency, and then try to find the time response of that. So you're dealing with a step input where the input is a step force, then applied to the muscle, and the output would be the displacement of the muscle itself. Let me just erase the whiteboard, and then we're going to do all these cases together. This is just going to serve as a way to recap everything we talked about, because each of these cases here is one of the cases we just addressed. Let's start with b equals to 9. Okay, so you remember from one of the lectures, we had a system that is this mass spring damper system again. This models a variety of different things. And you have a force being applied to it. In this case, it's modeling a muscle, and the transfer function between displacement and position is s squared plus bs plus 9. And b is the coefficient of viscous friction, mass is 1, and the spring constant here is 9. And this is just a constant. Remember the let's just do the first case where b is also 9, but let me just write here the standard form. Remember that the standard form is s squared plus 2 zeta omega n s plus omega n squared. That's the denominator of the transfer function. In the first case, b equals to 9. When b equals to 9, what is the damping ratio and what is the natural frequency? Well, the natural frequency doesn't depend on b, because we can directly compare these two formats. You see that I have 1 times s squared, 1 times s squared. 2 zeta omega n equals to b, and omega n squared equals to 9. So from this, we can always establish this relation here is independent from b. Omega n squared equals to 9. Omega n equals to 3 radians per second. This is for all values of b. In the first case, b equals to 9. When b equals to 9, what is the damping ratio? If b equals to 9, you can equate 2 zeta omega n to b, which is 9. So zeta is 9 divided by 2 times omega n, which is 3. 9 divided by 6, that's 1.5. What can you tell about the system now that we found out that the damping ratio is 1.5? What time of temporal response should we expect? Sinusoidal, exponential, both?
Exponential.
Only exponential. Only exponential, right? So this system has a damping ratio greater than 1. This is a overdamped system because this is greater than 1. And we only have exponential. What are the roots of this transfer function in b equals to 9? Are the roots real, imaginary, or complex conjugate?
They're real.
They are real. They are always real. And when you solve for the roots, that it would be s squared plus 9s plus 9 equals to 0. We have them here as s equals to negative 0.7 S equals to negative 0.785, that's one, and the second one is 1.14. These are the two roots of the system, right? Real roots, because the damping ratio is greater than 1, all makes sense for now. This means that we can rewrite the transfer function as a function of these two roots. Sorry, this is negative here. And both are negative. Of course, because the damping ratio is greater than 1, they must have negative real parts. We can now rewrite the transfer function as functions of the roots. How would that look like? 9 divided by what? What I put in the denominator? S minus this, so plus 0.785, S plus 1.14. When you multiply them out, we should get that. This is strange because when you multiply this, we don't get 9. So I think there's a mistake here. This should be 7.8. That's the only way you would get 9. So 7.85. Sorry. I'll double check the numbers. The numbers are not important. So 7.85. Now we multiply them. I'll go back there. So when you multiply this out, we go back here and you get the same function. Now we want to evaluate the step response of this. If you want to evaluate the step response, we need to multiply this function by the step function. What is the step function? What is the step function?
1 over S.
1 over S. Very good. Now we can take the inverse Laplace of this. How do we take the inverse Laplace of this? What is the first step? If you look at this in the table, we won't find it.
Partial fraction.
Partial fraction. How many partial fractions do we need?
2.
3, right? One for this pole, one for this pole, and one for the 1 over S. Don't forget that one, right? So, and the format of this partial fraction is easy: is A over this plus B over that plus C over S. So I'm going to give you the result here. Is 0.171 over S plus 7.85 plus, sorry, minus 1.171 divided by S plus 1.14 and plus 1 over S. And this is after partial fraction. We can now take the inverse Laplace. And what is the inverse Laplace here? What is the inverse Laplace? The first term, 0.171 exponential of negative 7.85t minus exponential of negative 1.14t plus 1. What do we see? We see two exponentials and we see a constant value, which is the steady state value. If we plot the time response, what should we see? We should see the system tending to 1. Remember that these two terms will eventually die to 0. And it goes to 1 following an exponential waveform. And this precisely characterizes what we defined as a overdamped system. Everything agrees. The system is overdamped, meaning that it only has an exponential component. This occurs because the poles are real numbers and the poles have negative real parts, which comes from the fact that the damping ratio is greater than 1. Any questions?
Professor, sorry, I some kind of forgot why here is multiplied by the 1 over s.
Because we are evaluating the step response of the system.
Oh, okay.
If you look at the question here, the last line says calculate in sketch the response to a unit step input for the following case.
Oh, okay, got it. Thank you.
Any other questions? Nobody? No? Okay. So if there are no questions, let's do the case where B equal, I think that's case number 2. Sorry, I went too far in my notes here. Case number 2 is where B equals to 0. When B equals to 0, what is the damping ratio? What is the damping ratio?
0.
0. Damping ratio will be indeed 0. And what should we expect to see as the time response?
An undamped system.
Undamped system, meaning that it will always oscillate. At which frequency will the system oscillate?
3 rads per second.
3 radians per second. Excellent. 3 radians per second. That's the natural frequency of the system, omega n. So if our calculations are right, we should see only an exponential, a sinusoidal component, or a cosine waveform, something like that, with a frequency of 3 radians per second. Let's see if we can get there. Oops, that comes later. Now B equals to 0. When B equals to 0, this function writes as 9 over s squared plus 9. B equals to 0, zeta equals to 0. And this characterizes a undamped system. If we want to do the step response, remember to multiply this by the step input, which means that we need now to do partial fraction. And how to do partial fraction here? How many terms we need for the partial fraction?
2.
2. 1 for s squared plus 9, which will be in the form of, because they have the square, as plus b divided by s squared plus 9. And another one for 1 over s, which is simply c over s. B in this case is 0, A is 1, C is 1. I'm going to skip the partial fraction because that takes too much time. B is -1. A is -1, actually. Yeah, A is -1. Sorry. A is -1. So we can rewrite A as C over S is 1 over S minus S divided by S squared plus 9. What is H of T? Is the inverse Laplace of that. What is the inverse Laplace of 1 over S? That's 1. And what is the inverse Laplace of S divided by S squared plus 9?
Minus cos 3t.
Exactly, minus cosine of 3t. Excellent. Haha, that's the 3 radians per second that we wanted from the natural frequency. So it is indeed a sinusoidal waveform oscillating at 3 radians per second with a shift here from 0. And where is this shift coming from? The shift is coming from the step input. The system will oscillate, but you notice that it's not going to oscillate around 0. Will oscillate shifted 1 unit up And that's because we are applying force and holding it. And the system then oscillates around the displacement of 1, not 0. Right? If we didn't have the step input and we just slapped the system, it would also oscillate, but it would then oscillate at 0. But we are now stretching it and moving to 1, so we will oscillate around 1. That's the step input right there. So if you plot this, what should we see? So this is h of t, and this is time. When time is 0, we have cosine of 0 is 1. So this is 0. And when you have cosine of 90 degrees, no, 90, when you have cosine of 2 pi, 180 degrees, this becomes -1 plus 1 goes to 2. So this oscillates between 1 and 2 like that. Yeah, centered at 1. All right, so this peak here occurs when cosine of 3t equals to -1. Means 3t equals to pi. 3t equals to pi. This gives -1. The system goes to 2. Interesting, right? So you see the exponential, there is no exponential. You see the sinusoidal coming from the fact that it is now no damping, but you see that it oscillates around 1, and that's because of the step input to the system.
Just a quick question about the whiteboard. Is that a G or a 9?
That's a 9.
Okay, thank you.
Everybody knows that that's a 9. Does that look like a G?
I think it's because the G under the B does look like a 9 a little bit. Yeah.
Okay. All right, well, that's a 9. Any questions?
Could you just go over again why we know that A is equal to -1, B is equal to 0, and C is equal to 1?
Well, we need to do the partial fraction decomposition here to get there. I'm just skipping that part. But we do need to now solve for A, B, and C using one of the methods we saw before. The easiest one in this case here would be to create a system of 3 equations and solve for it. So just cross multiply here, equate this to that, and then find the coefficients with S, with no S, equate them, S squared and so on, and then solve for the system of 3 equations. That's how we find -1, 0, and 1.
Okay, got it.
I'm just skipping that here because it's not the focus and it would take way too long.
Yep, makes sense. Thank you.
Any other questions? No? All right, so now let's do the third case where B is now 2. What is the damping ratio when B equals to 2?
1/3.
Is 1/3. Yep. Exactly. So we'll do that, but the damping ratio will turn out to be 1/3, which characterizes what type of system?
Critically damped.
Critically damped is when we have that equal to 1 exactly. Right? Hence the name critically, because anything lower than that becomes underdamped. Underdamped. Right? Critically damped is the transition between overdamped and underdamped. And what we just did here was a undamped system. Okay, so now B equals to 2. When B equals to 2, we have 2 zeta omega n equals to 2. Omega n is still 3. That doesn't change. Zeta equals to 2/2 times 3. equals to 1/3. So this is smaller than 1, and this characterizes a underdamped system. Underdamped system. So what should we expect to see as a result? What kind of temporal response do we expect from this?
A converging exponential and sinusoidal.
Correct. And why is that converging? Because this is less than 1, and the real part of the poles are positive or negative? Negative, right? The poles sit on the left side of the S-plane. Okay, so this means that we have now complex conjugate roots. And because of that, we cannot split this polynomial into any other format. We cannot, well, we could factor out the roots, but then the roots would be imaginary numbers. We can still do that, but it would be a little more complicated than what we want. But we could write this as a function of 2 imaginary roots. That's perfectly fine. Do partial fraction expansion with that, and then solve for the inverse, that works. But we cannot split this into real poles as we did before. So our transfer function will have to be split into partial fractions now, considering this polynomial entirely as it is. And when you do that, we'll need to write this in the format of as plus b divided by s squared plus 2s plus 9 plus c over s. And again, we can do the partial fraction decomposition, and you'll find the elements for the values for a, b, and c. I'm going to give them to you here. A is -1, b is -2, and c is 1. How do you do the inverse of this thing now? Well, this gets a bit tricky because, well, we know how to do, sorry, I wrote 1 over c, should be 1 over s here. 1 over s. It gets a little trickier because of this entire fraction. If you look at the table of Laplace transform, there are 2 important properties that we can use. The first one, where can I go? Right here. The first one is that the Laplace of a exponential of at cosine of bt is equal to s minus a divided by s minus a squared plus b squared. That's one of them. And then the other one is that the exponential of at sine of bt, that is b over s minus a squared plus b squared. I don't expect you to know this. I hardly need to look at the table to do that. And you see that these 2 are helpful because in the denominator, when you expand this, we have a second order function. Now we just need to prepare this function and then prepare the numerator as well. Now let's look at this. We have s minus a squared plus b squared. When you have s minus a squared and you expand this, we have s squared minus 2a plus a squared, s squared minus 2a plus a squared. So if you want to write this expression in this format, we need to somehow end up with s squared plus 2s. So what is the value of a?
-1.
It can only be 1. Very good. It can only be 1. So you can write h of the denominator of h of s as s plus 1 is squared. Right? So this will be s squared plus 2s, 2s plus 1. So we need to add 8 to it. There is no other option. because of this 2s, the only way to get 2s is to get 1 here. If you had 2, for example, 2 plus 4, it wouldn't work. So 2 plus 5 to get 9. So 2 squared is 4 plus 5 would be 9, but then it would have 4s. And here needs 2s. So the only option is 2. Which means that in the numerator, we also need s plus 1. So I can rewrite, let's rewrite this expression as follows here. Let me put it this way. Let me put a negative sign here and make this 2 positive, as it's still the same expression. So we have s plus 1 in the denominator. We need to make s plus 1 appear in the numerator, but we have s plus 2. So what you can write is s plus 1 plus 1. Yeah? Any questions? This expression here is the same as that. Nothing, and of course with the negative sign that I forgot in the front of it all. Are we good?
Yeah, looks good.
Yeah, okay, so now let's think about this. We see here s plus 1 is corresponding to this part, but then we have plus 1, which is corresponding to that part. So now you can split this into 2. H of s equals to negative s plus 1 over s plus 1 squared plus 8 minus 1 over s plus 1 squared plus 8 plus 1 over s. And now we have precisely this format and that format. Now we still need, so b squared here, we have b on top. So we need to fabricate somewhere here a b squared on top. What is b? B is a square root of 8. So if you want a square root of 8 here, we need to divide the function by 1 over a square root of 8. All right, so this gives us 1. We go back to what we had before, but now we have 8 square root of 8 on top. What is the inverse of this first part here? This first equation here. This corresponds to this, and it is h of t equals to negative exponential of negative 1 times t cosine of square root of 8t. What is the second one? Is negative 1 over square root of 8 times exponential of negative 1 times t sine of square root of 8t plus 1. And when we plot it, what we get, well, the plot's a bit complicated, but we know that it will settle at 1. We see that both exponentials are negative, and you should see something like that. Okay, so this is a underdamped system. You see now that in the time response, we have both exponential and sinusoidal components. We also see that the exponentials decay to 0, and why? Because the roots of, if you solve for the roots of this, the real parts are negative. The poles lie on the left side of the S-plane, and exponentials converge. So this is a map of all poles in this example. This is from B going from 0 all the way to 10. And this is where all the poles are located. When B is 0, we are here and there. See only exponential responses. And as B starts to increase, then the poles move towards the real axis. So during this entire path here, the system is underdamped. When you reach this point, both poles are the same. The system is critically damped. And as we start to increase the value of B, the system becomes overdamped, and these poles will now travel towards negative infinity, farther from, and more from the imaginary axis, and then tends to negative infinity. And the farther we remember from the first order system, the farther we are from the imaginary axis, the faster the system reaches the steady state, which makes perfect sense because in reality, we are increasing B, we're increasing the friction in the system, so the system will stop faster. Okay, I'm over time again, but I can take a question if there is any.
Professor, I'm just curious for this graph. So is there anything or any special for the intersection of the imaginary part and the real part?
What do you mean by the intersection?
Oh, like there's two lines, they cross each other, the point. So this point is anything special?
This point here, the center of the axis?
No, the two. Yeah, it's here.
This, yes, this precisely here is the critically damped point.
Okay.
Yeah, this is exactly the critically damped point because you see how the poles are moving, and when they get here, they are the same.
Okay.
Right? So at this specific point, theta equals to 1, the system is critically damped, and then they diverge